minutes. What is it? Recorder, and I have the picture gallery up. Nobody has their video on. I'm not telling you to do that. I just, one of these days I'm gonna meet you all in real life. I'm not gonna know what you look like. It's like, you're supposed to be a black box with your name on it. It's gonna be funny when that happens again. Let me get started. I'll share my screen and we will proceed with today's lesson. As a reminder, this Thursday, the 4th, 5th, 3rd, 4th, the 5th, we won't be having, I guess we will have, no, we won't be having class. I'll have your second examination prepared Thursday, and I will post it. I have to travel out of town to work on a research project in Junction, Texas. I know that sounds like a cop-out, that it's like, yeah, you're really going deer hunting, but that's actually not the truth. We are going to a house that's maintained out there by Texas Tech, and my job is unfortunately to, or fortunately, to program a little Raspberry Pi based data loggers that keep track of water flow by the different fixtures. So there's one attached to the kitchen sink, one in each of the bathrooms, one on each of the showers, toilets, and so forth. And I had them working more than a year and a half ago, but it took Texas Tech a year and a half to put in the computer network. That's kind of pathetic when you think of it. So now that the network is alive and running, we need to go back down there and need to hook those into the network. And Dr. Rainwater, you may know him, he is responsible for a different part of the monitoring system, and there's another person for a different part. So we're all going to go and turn all of our little gizmos on, and with any luck, we'll be able to remotely control this house. And then someday they're going to get people to live in it, and they're going to wonder why lights are turning on and off by themselves. It's not that. It's, I'm sitting there logging into the house to see what it's up to. Okay, well, so enough of that preamble. Let's begin. First thing, I don't know if, I haven't got an email, so I don't imagine anyone has noticed, but the content server died Friday night. Like at 11 at night Friday night. There was a big power shortage in my neighborhood. Transformers exploding, fire engines having to come and put out the fire. And the net result in my house was the server that had been serving content pretty much reliably for 10 years won't power up. So fortunately, I found a backup and I restored to the backups. I've reset all the links. So as long as you go in through Blackboard, you should be able to get to most of the content. Not all of it. One of the important things that did die was the online tools. They are kaput. So no more contouring packaging there. I have an alternate that works, but some of the stuff is completely broken. And that happens. And I'll be able to get it working again someday, but not, wasn't able to get it working over a weekend. So we'll go to lesson 21, and so it looks the same, but what you notice up here is it's not going to Atomic Kitty DDNS anymore. That's that particular dotted quad IP is a server in West Virginia, owned and operated by the Amazon company. So in addition to providing me with server space, they're going to try to sneak into your credit card and get you the Amazon Prime crap. Actually, they don't. They don't do resales on their web services, but it's fun to critique them for that. So that's the big change. And Web Tools now points to a $58 computer in my office that's probably fixing to die. and a lot of these are no longer functional, so that one doesn't work anymore. And I think we still have a contour map tool available, but none of the files are there because they were on a different machine. So we'll be able to get through the end of the semester without much ado. The EPA Net in a Box, I reprogrammed that to go directly to the host. So that looks like that's working, and Swim in a Box, that's working. So most of the functionality that I had created originally is still there. So today's lesson is detention pond simulation. And oh good, everything posted. We'll do it in the PowerPoint because that's a 2 megabyte download. That was really, God, that went fast. Very cool. So we'll look at a short PowerPoint presentation, and then we will I have a full swim example. We'll go to the Swim in a Box site, and we'll pull the necessary files across and take a look at the example. This example corresponds to the example that's in this presentation. So let's begin with the presentation. Yes, Matthew, the exam will be a very similar format. It's actually mostly programmed up. I haven't tested it yet to be sure that if you get the right answers, it records the right answers. But other than that, yes, and it's probably going to become active on Thursday morning, and you'll have 24-hour window to work on it, because I don't personally see that there's much of an issue to stick it to 3 hours. That's not that necessary. So let's go on with the presentation. So this is detention or retention basin hydraulics, and the purposes of a, damn it, every single day. Hello? That's my parole officer on the phone. So detention basin are used to mitigate peak discharges and provide water quality benefits. I don't have a parole officer. That was a scammer phone call. So let me start over again because I'm completely confused. Okay, detention and retention basin hydraulics. What are the purposes of a detention basin? Their main use is to mitigate peak discharges. We saw a photograph of a detention basin during the hydrology review for this class. That was the big old pond with all the houses around it. And what its purpose is to store water during a high flow event and then release it later so that the peak discharge of that high flow event is reduced to fit within the localized channel and drainage capacities. They're also designed in many cases to provide a water quality benefit. It turns out that putting water in a detention basin and keeping it there for a bit more than an hour has a fairly substantial reduction in nitrogen, phosphorus, and total solids or total suspended solids in the water column, and then the water is released on into the environment. And the first hour is huge, and then the remaining hours of storage, there's still benefit, but you don't get quite as much as you get in that first hour. So they used a lot for those fairly common water constituents. Don't want to call them pollutants because both the solids and the nutrients are important to the environment, but they don't want to have too much. So let's refresh our knowledge about nodes, because the simple way to model detention features using the SWM program is to do it at nodes. Unless it's a really very large basin and we have to be concerned with flow within the basin, we can simply treat a detention basin as a special type of node. So not an ordinary node as we have here, which have invert elevations, maximum elevations, and the possibility of flooding if we activate it. Here is a sketch of flooding at an ordinary node. So imagine we have these pipes flowing here, and as the water comes up in the pipe, it goes above the pipe crown or the soffit elevation up into our system. And here they're showing hydraulic grade lines joining different places. And in this particular one, here's the rim elevation at a manhole, and the water has come partway up the manhole, but it's not exiting out onto the surface. And we handle that with offsets, and we've seen that already. Then we go to a junction node where we allow flooding, and that's flipping a switch, and that is that switch is how deep is the flooding allowed and what's the ponded area. So that's our next complexity of conceptualization. And then we're going to go to a different type of node entirely called a storage unit or a storage node. And a storage node explicitly considers storage at the node. And it can include the subgrade portion of the node. And the storage node attributes that we supply are the same as an ordinary node plus a depth area relationship. We have a choice of a tabular depth area relationship, which is usually the most useful, or a functional depth area relationship, which is, in my opinion, of less practical use, but it's okay to start with because we can get everything kind of running and then go back and replace it with a tabular representation. Tabular one's the most useful and probably ultimately the practical one, but functional has its place. And these can be used for detention ponds, which is what we'll examine today, modeling multiple level inlet and outlet hydraulics, keeping track of riser inlets and an outlet that has a portion through a pipe or a portion over a weir or another pipe at a different elevation. And those bullet items will make a little more sense when we see a graphic. And let's go ahead and not click what I clicked on, classic. So as an example, let's consider that we have a detention pond that receives drainage from a 5-acre parking lot and then stores the drainage and discharges it into a nearby receiving stream. So when you take CE 4330, this is a fairly common component of the capstone design. You'll most likely you'll do it in HEC HMS or HEC RAS because that's what the instructors for that class know and expect. But you could do it in SWM, and here is how you might approach that. So we have a 5-acre parking lot, and then instead of going directly into a nearby receiving stream, we're going to run it through a detention pond. And let's suppose we've selected SWM as our tool to approximate the hydraulics. So we'll treat the parking lot as a subcatchment. We'll use the curve number method in SWM because it's pretty easy to employ. And we'll pick a high value for that, 98. So that parking lot is a pretty good generator of runoff. Any water that hits it, if it doesn't evaporate, is going to run off. And in this example, we're going to apply a 1-inch per hour storm for a 3-hour period. And we'll construct it hydraulically so that all flow passes through the detention pond before exiting to the stream through a 6-inch pipe. The 6-inch pipe is located at the invert of the detention pond, and then there's a 1-foot pipe at 2 feet above the basin bottom. So visualize, if you will, a side view of a detention pond. Let's go ahead and use the drawing. Oh, I don't have a drawing tool, which means that that is not, this is one of those days. Oh, there's a drawing tool. Where was I? There we go. And we'll choose a pen. What color do we want? Let's do it in white. So here's our detention pond. Here's our parking lot. So it rains on the parking lot, water flows over the parking lot, falls into our detention pond. We have a 6-inch pipe going to our stream. There's our stream. And a 1-foot pipe also going to the stream. I'm going to draw it up here in the air, but that may not quite be how we would really build it. So as the detention pond fills with water, once it gets some water in it, the flow will go down the 6-inch pipe. As it keeps filling with water, there's still flow going down that 6-inch pipe. Then at some point, the water gets high enough that it starts to go down the upper pipe. In this distance, in this particular example, is 2 feet. So that's what our problem statement is trying to express to us. The mental picture here is somewhat important. Sometimes you have to draw sketches like this to understand what you're trying to do. So here's a more fancy sketch. So this would be used if we're going to deceive them with color. We have our, there we go. We have Puffy the Cloud here, 1 inch per hour, throwing lightning bolts on our 5-acre watershed parking lot. And then that water makes its way to the edge of the parking lot, presumably into our detention pond, which we've shown here is a cylindrical tank, but the shape of the pond doesn't have to be a cylinder. It can be something that makes sense for the shape of the parking lot. And then the 6-inch pipe draining at the bottom, 1-foot pipe draining 2 feet up. In the case of our hydraulic model, we will let these two flows join each other at an ordinary node, a certain distance downstream of the pond, and then make its way to the outfall. So our components are Puffy the Cloud, subdrainage, a node, which will be our detention pond node, 2 conduits, 1 foot and 6 inch. The 1 foot has at least an inlet offset of 2 feet, and I'm drawing it here with an outlet offset of 2 feet. We'll see if we preserve that. And then the final modeler's trick is a large diameter conduit to connect to the outfall without surcharging. And so what that is our way of bringing these 2 pipes to the outfall. The reason we have to do something goofy like this is the computer program by design will only accept a single link to an outfall. So you have to combine all the links just before what you declare your outfall. So sometimes the outfall is not even at a real location, but it's at a hydrologically a hydraulic location that makes sense for the rest of the calculation sequence. And then we would do a swim model run. Here's a particular example here. And it has writing here that I can't read because it typeset it in white. So now would be the time I complain about Microsoft and Apple and everyone conspiring to make me look like an idiot. So this red shark fin curve up here, that represents what's leaving the subcatchment. So our 1 inch per hour for 3 hours, we're peaking out at about 5 cubic feet per second runoff, which makes sense, 5 acres. High curve number is essentially a runoff coefficient of 1. And so we should get the inches per hour multiplied by the area for the peak discharge. In the magenta line represents that 6-inch pipe. So water comes into the drainage basin and then the 6-inch pipe starts flowing almost immediately and produces this curve right here. The reason the 6-inch pipe doesn't go any higher is once there's surcharge on the 6-inch pipe, at some point you can't force more water through it. A teensy bit, but not much more. The blue curve represents the upper outfall pipe, that pipe that was 2 feet above the bottom. And so once the water gets deep enough in the basin, that outfall activates and starts carrying flow. The green line is the sum of the two outfalls, the magenta plus the blue curve, and that produces what we would observe coming to our outfall is the initial flow, then the peak, and then a long time as the basin drains and then it's empty. So if we look at the difference in these two peak discharges, without the detention basin in place, we would expect a peak discharge under those conditions of 5 cubic feet per second. But our detention pond reduces that to 2.5 cubic feet per second at the peak. Here's our detention pond depth area storage curve. And so at 0 feet, the pond stores 0 pool area. We get to 8.5 feet deep, and this is showing 80,000 square feet. So that's almost 16 acre feet of storage if it was a square-sided pond. So this is a pretty big pond to get that level of mitigation. And if I click view, nothing will happen because this is a picture. So let's first let's go visit that example, and then we will go look at another exercise example, which is actually going to be a homework problem. So it will be good to get through the two examples. Let me hit escape. And there's the data. I want to go to here. Would have been smart if I had written down the password. I think this is VNC pound TWO. It is. Close off Goodwin Street. Oh, this is not my usual computer. Okay, swim projects. Examples. We have example 1, example 2. So let's go here and get those data for the detention pond. I need the input file. Right click. Okay, how do I undo this? No, I don't want to do that. We just want to download the damn link. That'll work. Make a new folder. There we go. We'll start swim and then we'll go look at this example. File, open. All right, here's our example. It's identical to the one that was in the PowerPoint because it's the same example. So let's go look at the parts one at a time. First, we'll look at Puffy the Cloud. So there's our 3-hour storm. 1 inch an hour, 1 inch an hour, 1 inch an hour. Drops back down to 0. And it goes by the name 3-hour storm. Keep thinking of Gilligan's Island for their 3-hour cruise. Let's look at our subcatchment. So it receives the rain from rain gauge number 1, which is this object. It drains to outlet number 2, which is storage unit 2. The area is 5 acres. It's set at 500 feet wide, so that will control the timing behavior, if you will, for the runoff. Everything else is default outlet routing. We're using curve number hydrology, and the curve number is set to 98. There's our storage unit. We'll look at it in a second. It's invert elevation. It's at elevation 4. It's set to go to 6 feet deep. So when the storage unit's about to overflow, the water surface elevation will be at 10 feet. There's 2 pipes leaving it. There's the lower pipe, which is a 1/2 foot diameter, 6 inch, 400 feet long, roughness 0.01. And you notice the inlet and outlet offset are 0. And there's the circular pipe leaving it, 1 foot diameter, 400 feet long, 0.01 roughness coefficient, and it's set at a 2 foot inlet and outlet offset. And then these come to a common junction called junction 3, and its invert elevation is 2 feet. Max depth allowed is 6 feet. So when this 1 foot pipe just gets full at this end, we would be at 2 and 1 would be 3 feet of water there. And then here's our last link called the outfall pipe. It's a 4 foot diameter, so that's 4 times bigger than the biggest upstream pipe. And so that should accommodate the flow from those two without backing up. We set it to a free outfall. So at the outfall, at the end of this pipe, we're going to be at critical depth will occur at the end of this pipe based on the flow. So that's the setup. We go into our options. We see we have rainfall runoff, flow routing. Guess we should turn those on. Curve number runoff generation, dynamic wave. This one's set to run for 23 hours on go to 5-minute time steps. And they set the routing step at 30 seconds, and then we have that's automated adaptive time stepping. Variable time stepping will dampen the inertia terms. Normal flow by slope and Froude number. Our options are Froude number only or slope only. And our force main equations, Hazy-Williams, we're using the X-tran surcharge method. Choose OK. Let's let it run. That was amazingly fast. Let's look at the outfall. So the most we would expect is 5 cubic feet per second, but with the pond in place, we're expecting 2.5. And sure enough, 2.5. So let's see if I can remember how to draw the graph that's in the, before that, let's go ahead and get the two profiles. We'll go from here to here. And we're actually going to choose the path. Okay, there's our first profile. Upstream node, 6-inch pipe to the big pipe. Let me shrink this so it will fit on the same screen. And we will make another profile. Pretty much the same setup: upstream, downstream, so there's our 1-foot pipe. And what we will do is we'll look at both of the profiles side by side. I guess not side by side, top to bottom. So we know that there was a 3-hour storm. It starts at hour 1, so now we can see the water starting to fill up in the system. And our storage node at this point is storing water. According to the storage curve. So it's using a tabular type curve. And the table name is called detention pond because I have absolutely no creativity. And if we look at it, this is not specifically a shape of the pond, but it's intended to give us an idea of what the storage curve looks like. The horizontal axis, you can think of that as feet, and if you can imagine that this is 1 foot into the picture, so it's a thin slice, and it gives you a rough idea of the shape of the pond. So this graphic is intended to help you, the analyst, convince yourself that you're representing the pond the way you intend to. So we will continue, and at some point we're now activating the 1-foot pipe. If you look down here, the 6-inch pipe is completely full. It's still conveying water. But now we have water with the 1-foot pipe, and you'll notice that the hydraulic grade line is pretty much going from here and then dropping to that point to convey on it, flow onward. And in this diagram, the hydraulic grade line is pressurized until it hits the non-pressurized portion. And that's our drainage system. And we would conclude in the case of this one that, assuming that was the design storm we were after, our system is more than adequate for that design storm. And the purpose of the 6-inch pipe, quite frankly, is to actually drain the entire system. Because unless you're going to locate something like this next to mosquito rat acres, you want to drain your ponds after the storm, and a small diameter pipe will do that for you. It takes it a while. Here we are nearly 20 hours after the storm is over, and there's still drainage occurring according to this computer program. So that's how this graphic was made, and it looks like it was running on battery, was almost dead, and was just grabbing every graphic and getting it into a single screenshot as possible. Let's look at a different one. You're going to have a homework assignment coming up soonly. That's literally this. It's based on a detention pond in Harris County. It's governed by permit number 8-262-4, and it has a nice geometry. It's nice and rectangular. Has an overflow portion. The water comes in this corner, makes its way around these berms that aren't very tall, and then works its way on out. And then as it gets deeper, the berms no longer matter, and the water kind of can flow wherever it is. And these colored lines, this blue line, green, red, and magenta, represent the water edge at different elevations above the bottom of the pond. So the blue line represents an elevation of 140 feet, the green 142 feet, the red 144 feet, and the magenta 146 feet. Now, those are important because for the swim program, we need to supply the area associated with different depths in the pond. In side view, here is a sketch of the pond system. So it has a bottom of 139 feet as flow coming in, and then there's an exit pipe here at 4 inches, a different one here at 6 inches, 8 inches, and then an overflow channel. And so these values are taken from a problem statement. The real pond only has 2 exits. And so starting from the drawing, this is what we would start with. You have to study the drawings pretty carefully to figure out where the outlet is, unless you have the original drawing and they're big enough to see what's going on. So we have inflow here, outflow here. And if we use that to determine the depth area of the pond. So the easiest way to do that would be choose an elevation, find the pool area associated with that particular elevation, and then record the depth and the area. Usually the depth would be in feet. The area will be in square feet, unless we're doing HEC HMS or HEC RAS, we'll do the area in acres. So here's the first one. We have a pool elevation of 140 feet. And so the water pool would look like that blue object right there. And we would need to measure the area of that in acres or square feet. We measure acres, go into square feet, it's real easy. So the tool we would use to measure this area is the same as we did when we were measuring areas for the hydrology part. Acrobat Pro or something, and you would just measure the area of the enclosed object in some units and then compare it to a known unit, and that would give us pool area. And the nice thing about rectangular ones is you can almost do them on a hand calculator. So this first one, for example, the pool area is 0.25 acres. Then we go up to 1.5 feet of depth. The pool elevation is 141 feet above the datum, and the area associated with that is 0.35 acres. Then we go up again to 2.5 feet of depth, pool elevation 142 feet, pool area 0.55 acres. And each time we're measuring the area of that particular boundary. Then we go to 143 feet of pool elevation, 3.5 feet of depth, 0.7 of an acre. 144, 4.5, 0.9 acres. 145, 5.5, 1.2 acres. And just about to overflow. Pool elevation is 148 feet, and the depth is 8.5 feet. The pool area is 1.85 acres. And if we were to go any deeper, it would start to overflow to neighboring properties. So we'll go back to that again because I always think it's cool. So all we're doing is getting the surface area associated with these different water levels. Once we have that, we can enter the information into SWM and then apply rainfall and simulate the pond filling and draining outflow hydrograph. And see if I can, I think I have that example built already. This one. Okay, it's going to be right there. I'm going to have to remember what the name of it is. Oh, it's not on this computer. That makes it even harder. So let's see if it's on this one. SWMM -FILES, cap F. That's the one we just looked at. And Bear with me because this is worth 2 dash exercises. Detention ES 15. Provisional. Oh, sweet. Okay, here's the same one. And I just wanted to make sure that everything was there. And let's see if there's an explanation in the workflow notes. So here's the what we're about to simulate. We're going to have a basin that has a 12-inch inflow coming in at 139 feet and a 4-inch outflow at the same elevation. At 141 feet, there's an 8-inch pipe brought in, 145, another 8-inch pipe, and 146 feet, we get into a 2-foot wide, 50-foot wide rectangular swale. That's our emergency overflow. So our next step would be to capture the image into a PDF, which is done, and then use measurement tools to find the area of the big square and then the other squares as we move to different elevations. And then we'll make this conversion table. So we've measured these elevations, which correspond to these particular depths above the bottom of the pond. We've got an area here in acres and then converted to square feet, and we'll put in the square feet and the depth into SWM. So here's our SWM model, which we'll go to in a second. And then using some of the problem supplied values, we can explore the behavior of that detention pond. Let's create a new folder. I really need to give it the right name. And I don't have it handy, so let's go get it back from here. (8.262-4). Okay, and then we will go and grab the input file. And unfortunately, I don't have a base map to use, otherwise I would. Because we can't load the PDF into SWM and have it work. Okay, so we'll start SWM again, and now we'll look at our other detention pond. Open. And there's the detention pond, and let's go look at the parts. Now, if we had all the information on a piece of paper, building this is not all that hard. And what we're doing here is economizing on time. We have it already built. If we wanted to modify it, that's not hard either. And this gives us the building blocks to make as complicated a network as we need to. So we'll go look at our rain gauge. So this is a 3 inch per hour. For 6 hours. 1, 2, 3, 4, 5, 6. So that's a pretty good storm. Even in Harris County, that would be uncommon. And we'll look at our subcatchment is a watershed, 9 acres, and this is supplied elsewhere in the problem statement. And the percent impervious is taken care of, and that routes to our storage unit. So you can either consider the storage unit to be the watershed. Oh, actually, the storage unit, this first storage unit is the watershed. The second one is our detention pond. We connect to it through a 1-foot pipe, which I think is what the drawing had. Yep. So using a storage basin to represent a whole watershed is also a common trick, because that lets us keep storage on the watershed and then drain it into our system, or we could direct connect. This is the pipe that connects to our detention basin. And if we look at our detention basin, its invert elevation is set at 139 feet. It has a tabular storage curve. We'll investigate that in a second. It drains through up to 4 different outlets to a 138.9 foot junction, which can take on a maximum depth of 9 feet. And then that junction drains through a 6-foot diameter pipe to an outfall. And so all this downstream stuff could be changed to fit a broader network. This first part is just to get our detention basin working the way we anticipate it should. Here's the overflow swale, represented as an open rectangular. So 2 foot deep, 50 foot wide. And then our first, oh, somebody has decided to join me. Then our first conduit, our 8-inch diameter circular one. Our second one, also 8-inch circular. Our third one, quarter of a 4-inch diameter. And if we examine the offsets, the 4-inch has no offset. The lower 8-inch has a 2-foot offset inlet and outlet. The upper 8-inch has a 6-foot offset inlet and outlet. And the swale has a 7-foot offset inlet and outlet. So if we were to create a profile, and let's see what it comes up with. It's going to do the upper 8. Should be good enough. Let's do another profile. Wait. And one more profile, we'll get the bottom. So there's our 3 profiles. And the trick becomes how to organize them so that you can visualize. So that's our bottommost one. Let's make it about that size. Our second bottommost one. Then our all right, that should be viewable. So now we run our simulation. It's completed. Let's see what we just did before we move on. Rainfall runoff, flow routing, dynamic wave. 23 hours, 5-minute and 15-minute time steps. Ignore inertia, Froude number, Hasey-Williams, X-strand. So that's what we ran. And now we'll go. So now our storm begins. Rainfall begins. Rain, 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 rain. And then runoff begins. And you'll notice that our detention pond is taking on water. And we can't see this well here as I wanted to. There we go, that'll work. The bottom pipe is pretty much carrying flow almost right away, which makes sense since it's at the invert. And we don't see blue down here because that pipe is so big, the flow thickness is too low for it to be able to render in the graphic. But our bottommost pipe is now surcharged. Hour into the storm. We've been storing water for an hour and 45 minutes, and now it's starting to flow through the second pipe. And I think the second pipe is enough to take everything. So we don't actually fill much beyond the top of the second pipe. And that's how detention ponds are simulated using the SWM program. So the only real piece remaining would be pumps. And I will find some examples of pumps in SWM and present them a week from now, Tuesday a week from now, and then we'll move into collection systems. Sanitary collection systems. Most of the computational tooling that you would need has been presented. So you had EPANet for pressurized systems, SWM for open systems, and you've seen little pieces of bigger systems demonstrated. And we can look at a fairly extensive one if I can find it. Spend a lot of time going in circles, don't we? Okay. I wonder if lesson 20 had that does not have the one I was looking for. I have one of the Marcia Sharp Freeway here in Lubbock. That's a pretty extensive SWM model, and that would be a good one to show all the different parts working together. But I don't think I have it handy. So what am I for time? I got 20 minutes to go. Not that one. We'll see if we can't find it, get it uploaded, because it's worth looking at. File, new window. MSF. Cool. Now all I gotta do is see if I have a, actually I always meant to upload this to the class website, so let me see if I can figure out a way to do that. Got a backdrop. Hope we use the PL44 current model sets. All righty. Hope this isn't too big. 300 megabytes. Wonder how long that's going to take. Should take 100 seconds, so about 2 minutes. So what we'll do is we'll upload it there. Let's get prepared here to actually receive the data. Hopefully it's in the memory. It's not. There's swim. Water systems. Okay, and it was called SW files. And it's still uploading. So as soon as it's arrived, we will unzip it, and then we can go look at an example that invokes all the pieces of drainage that we've been talking about for the last 4 or 5 weeks. I'm going to go ahead and look at the, would you be willing to rebuild that example right now? Yeah, I guess so. Let that thing run in the background. So there was a special request to watch me foolishly attempt to rebuild an example. I will go ahead and give it. So which example? That's kind of important. The simple one or this one that's on the screen right now? I was referring to the one on the screen. Okay, let's go ahead and we'll do that. Let me get all the support materials I need to have handy. So even though I make it look like I do this stuff willy-nilly, I actually don't. So I'm going to need, oh, I don't have the table handy. I'm going to need the depth area information. So I'm going to ask you to let me cheat a little bit here. Let me take that. Copy that, and then I need a place to write it. Oh, wait a minute, it's just a text file. Let me put it right here. Okay, cool, it's on the clipboard. So what I put to the clipboard is this is the depth column, and then this is the ponding area that's associated with the different elevations here. So as the pond goes up, look on the right, you see the depth is increasing. Actually, I guess I could do it directly from this, except I still have to convert acres into square feet. So, okay, we can rebuild from scratch. So I don't want to clear that. That's in case I screw up. So in case I mess up, I have everything as a backup. So file, exit. Sure. So we'll start swim. We're going to build a brand new one. Let's give it a name. We're going to call this 8-262-4 live. And I guess I need the rest of the problem statement. I don't know what the drainage area is, so I will start with a drainage area. There's my drainage area, and we'll parameterize that shortly. Then we're going to have our storage unit. And we'll have another one certain amount downstream, and we'll connect that to our outfall. So drainage area, detention basin, collector node, outfall node. Next thing we'll need to do is we'll let's actually mess with some of the defaults here. we're going to have to manually change everything at some point. Let's get my flow units into, see, those are inches per hour. Let's get them cubic feet per second. We're good there. Now we'll set our options. We'll have to turn on these processes when they become available. We're going to use curve number to do our runoff generation. All right, so we're pretty close to set up cubic feet per second. We're going to need Puffy the cloud right there. So there's all of our pieces, and now let's go start drawing conduits. So I'm taking advantage of the drawing tool to let me draw things that are in some sense parallel so I can see them. And I'm not going to put the rectangular in right now because I don't think I need it. I might as well just do it. Okay, so that's all connected. Let's take our subcatchment and we'll just do the defaults, but the outlet is going to be storage unit 2. Rain gauge is going to be the one and only one that we have. Let's see what we have to choose from. We have 1. And everything else we'll just leave as is for the time being. So you notice this dashed line is connected to our outlet. So in this case, everything is going to go into this storage unit. Keep in mind, I don't have a separate storage unit to represent the watershed storage yet, and you'll see what the impact of that is when we run the simulation. Next, we need to set our rain gauge up, intensity. So there's how we set the times, and then I think I was using 1 inch per hour. I'll actually just start everything at 1 inch per hour. 1, 2, 3, 4, 5, 6. I think 3 hours should be enough to drain it. Take a picture of it. Inch per hour until hour 6, and then it drops to 0 at the end of hour 7. She's okay. So our rainfall's been taken care of, and next we have to deal with invert elevations. So let's go back at our initial analysis. Our invert elevation would be 139.5. That would be at 0 depth, 139.5. And let's let things get to 10 feet deep. And we will have a tabular storage curve at some point. And we need to give it a name. my pond. So something like that to get the depth, and then we have to supply areas. And that's where we would, again, refer back to our analysis. So at a depth of a ½ foot, we're at a ¼ acre, so that's about 10,000. 43,000, quarter, that's 10. So there's our ½ foot, 1 foot deep, 1½ foot's 0.35 acres, and so on. This is where I'm going to actually exercise my privilege of cheating. And so 1 foot deep, I'm at 97.43. At 3 feet deep, I'm at 19.410. 5 feet deep, 32130. 7 feet deep, 67600. And between 32 and 67, we could interpolate if we wanted to. Let's just make it 43560. So that's a full acre right there. Between 19 and 32, be 25,000. And then this ½ footer, the 1 foot's the one we're going to need to jack with. 9,000 and 19,000, 9 and 5 is 14. So there's our approximation to the depth area. And for an actual one that you're doing, you would have time to actually do these calculations precisely. Let's take a look at it. Yeah, that looks about right. You notice these straight walls here at the top, and that makes sense because of the way that the pool area doesn't change. So all the storage at this point is contained in depth, which is okay. So we've selected the curve name, we told it tabular, our storage thing is done. Our next one is going to be to examine the different elevations, 139.5, 141.5, 145.5. So this one's going to be 0 offsets. This next one is going to be at 2 foot offsets. Next one, 6 foot offsets. And the last one is at a 7 foot offset. Set this elevation, something like that. And I'm making numbers up now. So we're not ready quite yet, but we can attempt a simulation, see if we have broken pieces. Actually, that's pretty amazing. Let's look at this bottom pipe. and that makes sense. Pretty sure the top one will have no flow in it. And that's it. I have to end class now because I have other obligations. But I'll leave this up here and we can pick it up our next face-to-face meeting. And you'll have a problem very similar to this as a homework exercise, which is probably the motivation for asking me to do it live, which is fine. That's good. But the key thing is I connected a rain gauge to a watershed, to a storage unit, to the various flow conduits, all the way to the outfall. Let's go ahead and save it. Exit. Exit the connection. Close that. Wrong one. Let's see. That was weird. Stop sharing, and I want to wish you all a great great day, and have a good week. Have a good weekend. Take care. Bye-bye.